All right, good afternoon, everyone. We're going to jump through the QLearn solutions. Now, forgive me, my dog is behind me. He might bark at me because I'm not giving him attention. It's also going to be a little bit inconvenient going between the eraser and whatnot, but that's okay. We'll work through it. Point is that you guys have got these solutions here. Keep in mind that this is just a screenshot, so your numbers will be a little bit different. So, for example, this first question -8, yours might be something else entirely. Just being aware of that. All right, let's jump into it. For this question, we are asked to calculate the specific latent heat of vaporization. Now, that point you should remember, well, that's my equation for vaporization. Q is equal to mL, Q is energy, and M is my mass. From this question, it's also super important to write down the information that you're given, and that being that the mass is 8 grams. Okay, now, important also to read the full question. You're asked to find the latent heat of vaporization in joules per kilogram, which means I need to convert this, that's not an 8, to kilograms, just like so. Excellent. Now I'm also asked to find latent heat of vaporization. We've got two sections where latent heat applies, right here and right here. Now we need to be able to identify which section does refer to vaporization. Now here, in between here and here, that is when we have liquids turning into a gas being a vapor, so this is the section that we are looking at. Now, if we want to use this equation, Q is equal to mL, we need to know what is Q actually equal to. Well, we can read our graph. Our x-axis, that's energy supplied in joules. The y is temperature, T, this one is Q, so we're going to have to read how much energy from the graph. If I go all the way down from where the latent heat of vaporization starts, right there, that appears to be about 950 joules. If I look at the ends, it's a little bit over that little square here, a bit over 3,200. Maybe it's exactly 3,220. We wouldn't penalize that harshly. So let's take a look. Our Q for this region is going to be the maximum take the minimum, 3,200. Our max minus that minimum amount is 950. That's going to be 2,250 joules. And now we've got everything we need. Q is equal to mL. So 2,250 is equal to 0.008 L. Remembering we needed to convert that to kilograms. Divide by that on both sides. 0.8. And that's going to give us our answer. Now, I don't have a calculator on me. Where would the closest calculator be? I'm going to turn on my computer and go on to the next question in the meantime. All right, let's take a look. Question 2, we are asked to calculate the average mass specifically for 231,000 joules. That's this section right here. I'm reading that that's my energy in joules. Cool. So I need to find out what goes in this little spot here. Now, average, the equation is the sum of all of your different digits divided by the number of digits n. So I can see that I've got 101 plus 101 plus 104. Your numbers might be different. And I've got 3 numbers. Add them all together, and that should be like, what, 101 point something? 102? Let me get my calculator up. So this is off screen, by the way, you can't see me adding these up. 101 plus 101 plus 104. Divide that by 3, our answer is 102. Okay, so that's our average. So that's the answer right there. 102 would go into the answer box. Now I can also do this question quickly. 2,250 divided by 0.008. So our L is going to be equal to 281,250, and this is joules per kilogram because we were asked for that specific unit. So that's what we would put into the answer box, 281,250. Let's continue to question 3. We are asked to find the absolute uncertainty for the average mass when there's 143,000 joules applied. So we have to look at the energy section, 143,000, that's that row there. Now we know absolute uncertainty, we know our equation, we could look at our formula sheet. It's going to be max take min divided by 2. Now looking at this row here, I can see the maximum amount, that's going to be 66. The minimum is going to be 64. So I'm going to divide that by 2, chuck it into the calculator, and the answer is going to be 1. So that's your answer, 1. Easy peasy. Now, this one is a bit of a trickier one. That's okay. In fact, I might even do the next one just because it is a trickier one. You guys have to remember, what are these two areas called? When it's turning into a gas, it's turning into vapor. So that is vaporization, either with American or Australian spelling, either way. And this one over here is when we've got solid liquids and solids. That is fusion. Okay, so those are our two areas there. Let's come back up to this one. All right. Student conducted an experiment to determine the specific heat capacity of an unknown substance. So that's probably what we're going to be trying to find, which weighed 0.32 kilograms. Let's start writing that important information. M is equal to 0.32 kilograms. They modeled the temperature T against the heat applied Q, as T is equal to blah, 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 blah. And we're given some kind of equation, 0.09 Q plus 40.1. Now take a look at this. They noted the initial temperature of the metal was also 40.1 degrees Celsius. That's the number we just got there. And that's an important concept in physics as well. When we're looking at these linear models, T represents Y, that's our gradient, so Y equals mx plus C. C is the y-intercept. But in physics, it's actually the starting value. It's the number that you actually start with. So we've got that the initial temperature is 40.1, and that's how that's incorporated there. Excellent. Deduce an experimental value for the specific heat capacity C. So we don't know what C is. We want to figure it out. Okay. Now we know a relationship to figure out C. We've got Q is equal to MC delta T. Okay. We're asked to find an experimental value. So somehow using this equation from our experiment, we should be able to get what is C equal to. Now I can already see some familiar terms. I can see a delta T here, but there's a T over here. So I'm going to have to change something a little bit. So I'm going to work with this one because I want this equation, I'll call it 1, to look like equation 2. So we need to work it a little bit so that, for example, Q is on the left and T is on the right, and it has to become delta T as well. So first things first, I can see that there's no other added terms. See how over here we've got plus 41? There's no other constants. So let's start by taking that to the other side. But I'll just rewrite this whole stuff first. Put it over here. T minus 40.1 is equal to 0.09 Q. Excellent. Now, hopefully, this is looking a little bit familiar. So TF minus TI, because that's exactly what 40.1 is. That's our initial temperature. So I've actually got the equation for delta T. TF minus TI. That's exactly what we've got right here. So I'm going to rub that out. Now that we've remembered what is delta T equal to. I haven't changed anything on the right yet. But I can rewrite this as delta T, 0.09 Q. Alright, so that's looking good. We've gotten rid of that constant. That's great. It's just incorporated inside of delta T. It's a difference in temperature. We don't care about the exact temperature, just the difference. But I can still see that my temperature is meant to be on the right and energy is meant to be on the left, but right now it's flipped around. So we're going to have to flip that as well. To do that, we're going to divide by delta T on both sides, and also divide by Q on both sides. That's going to cancel there, and that's going to cancel there. We'll be left with 1 over Q. Whoa. Hopefully you didn't hear that. My dog's just taken down a poster. Good on you, Oreo. That was a bit scary. You a little bit scared, Oreo? You okay? That was crazy, wasn't it? Shouldn't be playing around. Alright, let's get back to it. He's a bit startled. 1 over Q is equal to 0.09 over delta T. Excellent. So we've now got the Q and the T on the right side. Q's on the left, T's on the right. But this is currently the reciprocal. It's the inverse. We've got Q on the bottom when it's meant to be on the top. So we're going to flip that fraction. Q is equal to this one over here, just like this. Because we're flipping our Q and also our T, we're not just only flipping them, we also have to flip that gradient. So the gradient ends up becoming flipped as well, just being aware of that. Awesome. So this is now looking really, really good. I can rewrite that other original equation. Q is equal to MC delta T. And these are looking exactly the same. The only difference, if I can change my color, is this section here. Oops, I didn't rewrite my top one very well, did I? Because I forgot that that's now delta T, just like we had here. I rubbed it off by accident. Okay, which means if everything else is the same, well then the part in the brackets must also be equal. So 1 over 0.09 is equal to MC. Now the M here this is actually just our mass, which we were given in the question, is 0.32 kilograms. So now we can start substituting in some values. 1 over 0.09 is equal to 0.32, I think I said. Double check, 0.32. Excellent. Great. So I can also simplify the left. 1 divided by 1.09. Nope, did that wrong. 0.09. That's equal to 11.11 equals 0.32c. So let's divide by 0.32 on both sides. That's gonna, nice. Cancel that out. So C is equal to 11.111 reoccurring divided by 0.32. Therefore, C is equal to 34 point, bit clunky, 72. Now that's a really high number based on another example I did today. So I'm just going to quickly check my math. And the numbers that I've got are correct. 0.32, yep. Put that over there. Excellent, we found delta t. I've copied the gradient right, haven't I? 0.09, excellent, yep, that's cool. 0.09, yes, yes. Let me just double check I did this right. 1 divided by 0.09 is in fact 11.111, and then divide that by 0.32, and that will get bigger, which is 34.72. Excellent. The final thing is our units. Because I used kilograms up here, this is going to be joules per kilogram degree Celsius. And hopefully I specified that's what I wanted the answer in, joules per kilogram degree Celsius, and round to 2 decimal places. So this is going to be 34.72 for me. Great. So we've done those two. Bit of a tricky one, that one, but we did it. Let's take a look. A student conducted an experiment to determine the specific heat capacity of an unknown metal. They measured that the metal is 6.35 grams. The student placed this in some water. It was boiling. And we got the specific heat capacity of water and allowed enough time for it to cool. The student then moved the metal to 183 grams of cooler water, initially at 18 degrees, and then it obtained equilibrium at 24 degrees. Calculate the amount of energy that the metal lost. Okay. Now we've got two different substances here. We've got the metal, and we've also got water. I'm going to separate the two. It's important to write out all of our information. So the metal's mass is equal to 6.85 grams, which we could also convert to kilograms if we need to. Here, look at this. Our C is in joules per kilogram, so I will convert it just so that we're all got the same units. 0.00685 kilograms. Great. Now, I don't know the specific heat capacity of the metal. I haven't been told it. And I do know the temperatures. So the final temperature, that becomes at equilibrium at 24 degrees Celsius. So 24 degrees Celsius. Do I know the initial temperature? Well, there's no numbers for the metal. I can see that the water was initially at 18. But if I read the section here, it was placed in boiling water, the metal that is. The metal was placed in boiling water and it reached equilibrium. So the initial temperature is actually 100 degrees Celsius for the metal because it was boiling. It was the same temperature as that boiling water. So that's one part. We've also got all the water here. So the water is 183 grams of water. M is equal to 183 grams, which is 0.183 kilograms. Because remember, specific heat capacity of water is given to me, 4,180 joules per kilogram degree Celsius. Great. And now we can do our temperatures. Ti is equal to 18 degrees Celsius. The final temperature is the same as the metal because they're in equilibrium. So that's 24 degrees Celsius. Great. Okay. Now, what are we actually asked to find here? Calculate the amount of energy that the metal lost. Well, here's all our metal information. We want to find the amount of energy that was been lost. Q equals mc delta t. We want to know what Q is. Q is equal to, something? We don't know. But if I look at all my variables, I know the mass. There it is there. I don't actually know what C is. So I actually can't do anything with this metal yet. But we've got all this extra information, so maybe we'll be able to use that. Now, I've given you guys a hint here. Energy cannot be created or destroyed. The energy lost has to be equal to the energy gained by something else. The energy that the metal has lost is equal, let's do it down here, Q lost is equal to the energy gained by something else. The energy that the metal has lost is equal to the energy gained by the water. And now we know what Q is equal to. It's equal to mc delta T, but this side of the equation is all about water. So let's use the water's information. So the mass is equal to, in my case, 0.183. That's at kilograms. The specific heat capacity, I've got that for the water, 4,180. And they're in the same units. And then our final temperature, sorry. Let me zoom out, zoom back in rather. Our difference in temperature is TF minus TI. TF, let's do it up here. Delta T equals TF minus TI. That's going to be 24 minus 18, which is equal to 6. So that's equal to 6. Chuck it in the calculator, and that's going to be our answer. 0.183 times by 4,180 times by 6, 4,589.64 joules. Excellent. And there we go. That's how we would solve that kind of problem. Now, yeah, excellent. Great. Question 7. Is there any other easy ones we can just kind of bang out? Oh, this is a nice one. We've done a lot of hard work. Let's break it up with an easier one. A student conducted an experiment and measured that the specific heat capacity of a metal is 9.2 joules per kilogram per degree Celsius. So the measured value from our experiment is equal to measured specific heat capacity, 9.2 joules per kilogram degree Celsius. They then looked online and found that the closest specific heat capacity, so the accepted value for the specific heat capacity is 7.9 joules per kilogram degree Celsius. Calculate the percentage error. So now we've got to remember that equation. Percentage error, not pocket addition, percentage error is equal to measured take accepted divided by accepted times by 100%, technically. You don't have to, of course, do the percent sign, but that's what it means. All right, let's do that. Measured, let's substitute in our numbers. 9.2, 7.9, 7.9 times 100. If you're doing it in the calculator, make sure you're doing this in brackets if you're doing it all as one line. Otherwise, it won't know what you mean. So 9.2, subtract 7.9. You could separate it like this. This ensures that you're not going to get anything wrong. So that's 1.3 divided by 7.9 times by 100. So that's equal to 16.455%. 7%. And how many decimal places do we want? 2 decimal places. So 16.46. That is our answer. 16.46. All right, let's do this one now. We are asked to identify a mathematical relationship between the energy added to the corresponding mass of the substance. When we're asked to find a mathematical relationship, that's not when you're identifying the overall trend. I actually want to see some numbers, and I want to see some variables. I've even given you a hint. Remember to ensure that your final answer is in terms of Q and M. You can see these sections here, they don't have Q or M in them. All they've got is Y and X. But because you're asked to find the relationship between energy and mass, I expect it to be in terms of Q and M. All right, so let's do it. This is when it's going to look something like this. Y is equal to M plus or minus delta M X plus C plus or minus delta C. Now, those deltas mean uncertainty. So we've got the gradient plus or minus the uncertainty in the gradient, and then the y-intercept plus or minus the uncertainty in the y-intercept. Alrighty. Let's start calculating some stuff. Oh, before I do, let me clarify. M and C, these come from your line of best fit. Line of best fit. It's the best guess at these values. Like that. Our M, so we're going to look at this one here, is equal to 0.004. 0.0004. And then our C is negative 2.33. So we've already done some of the work for us. We've got this one, we've got this one. We could also do Y and X. Y, that's just the value on the Y axis. So that's mass. So Y is going to become M. Not M for gradient, M for mass. So I'm not going to change that in just yet, just so we're aware though. Energy, that's our x-axis. That's going to be Q. That's the variable for energy. So Y is going to become M, and X is going to become Q. But we'll do that after, because we need to find delta M and delta C. Delta M, absolute uncertainty. That's max take min divided by 2. Now I'm going to make this more specific to say it's the max gradient and the minimum gradient. So our max gradient, that comes from the line of max slope. So our maximum gradient is 0.00041. Our minimum down the bottom, min slope, 0.00039 and divided by 2. And that's going to give us an answer of 0.00001. So that's delta M. Not too hard. Delta C is very similar. Very, very similar. Delta C is going to be max C, our specific heat, not specific heat capacity, our y-intercept, divided by 2. So the maximum one, again, comes from the line of max slope, minus 5.14. And now we've got a minus, and it's going to be another negative number. So in brackets, minus 1.33. Because the equation has a minus in it, it's a negative, but then so does our actual number. So that's why I've done that in brackets there. And then divide by 2. Oh, I've forgotten something. Ben normally reminds me. Plus or minus all the way through. Plus or minus, plus or minus, plus or minus, plus or minus, plus or minus. And our final answer will be plus or minus. So let's take a look. Let me reset my calculator. Let me pull up my room. All right, so we've got minus 5.14, and then that's going to become minus minus, which is a plus 1.33, and then divided by 2. So I get the answer of negative 1.905, but because we've got plus or minus, it doesn't really matter about that negative there. Now, with our significant figures, we should get in the habit of rounding to one significant figure. That's going to be 2. But you will be okay if you just rounded it to 2 significant figures. So 1.9, that would be fine. That would be acceptable. All right, we've done a fair bit of work. We need to put it into this format now, up here. So Y, this is where we can finally state our final mathematical relationship between the energy added and the mass. Y is the mass. That's our y-axis. So the mass is equal to, we've got our brackets, so our gradient from our line of best fit is 0.004 plus or minus, did I do the right number of zeros? 3 zeros, sorry. Plus or minus delta M, we calculated it here, 0.00001. And now we need to put in X, in this case, it is Q. What's up, Ario? You're sad for some reason. Minus our C value, that's here, minus 2.33, plus or minus 2. And that's our answer. We can round this to one significant figure because we've done so here. Well, not one significant figure. It has to match whatever our place value was. So if this was, for example, 0.2, we would round that to 2.3. But because this is in the ones column, we're going to round that to 2. But again, not going to be too critical on that. So there you go. That is a final answer of a mathematical relationship relating mass and energy. I'll come back to that one. This is an easy one. The overall trend. I'm going to say, if this is all my data points, I'm calling that pretty positive relationship. Remember, I want to see 2 things. Number 1, type of function. Type of function. In this case, linear. Direction is the other thing. Is it going positive or negative or inversely proportional or directly proportional? This one is absolutely positive. Now, there are a couple of other options in this multiple choice. And if we take a look at the actual graph, there are distinct areas where we're getting absolutely no change. So that tells me that that's incorporated within the actual trend of the data. Every so often, we're going to have actual plateaus because they're not just random; they occur quite periodically. So I'm going to say that this is positive and linear. Oh, not with no gaps. I think I've cut off the screenshot. That's okay. The correct answer would be positive and linear with some gaps or plateaus. Positive plus linear with some gaps and plateaus. Blah, 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 blah. Tick. And that's what it would be. This one here. I conducted an experiment and measured the specific heat capacity of a metal to be 0.32 joules per gram. Then we take a look at here, because what we're asked to do is identify the most likely substance. Joules per gram, degrees Celsius. So it's the correct units. We just have to compare which one of these is closest to 0.32. Looking through the whole thing, oh, this one's pretty close. This one's kind of close. So is this one. So you might say something like, to compare them, the two closest elements are, well, zinc is clearly one. Zinc, and this is way too big. So either zinc or tin. And you might even put their specific heat capacities in there. 0.387, and tin, which is, let's include the units too, joules per gram, degrees Celsius. And tin is 0.213 joules per gram, degrees Celsius. And then you might make an actual deduction. Because, and hopefully you can do some quick math, 0.387 joules per gram to degrees Celsius is closer to 0.32 degrees Celsius than the most likely one, zinc. Most likely zinc. Ta-da! Excellent. All right, how many more questions we got? We have not too many, 3 to go. I'll come back to that one because we haven't done this one yet. A student conducted an experiment to determine the specific heat capacity of an unknown metal. Okay, so it's very similar to the one we did earlier. We're going to separate our variables. Metal, water. The metal has a mass of 0. Oops, sorry. I'm not going to jump ahead of myself yet. 5.54 grams. But I already know I'm going to have to convert that, so I'm going to do that now. 0.0554 kg. Do I know the specific heat capacity? Let's take a look. No, I do not. Calculate the specific heat capacity of the metal. That's what I'm trying to find. Cool, I can do that. Do I know Ti, the initial temperature? Well, because I've done the question already, I know that it's boiling. So it's at 100 degrees initially. The final temperature, I know that because I've done this experiment, so have we chuck this really hot piece of metal into a cooler piece, and then it obtains equilibrium, in this case, 22 degrees Celsius. So that's for our metal. Our water has got a mass of 0, I did it again, jumping ahead of myself, 149 grams. 149 grams, which is equal to 0.149 kg, dividing by 1,000 if you don't know how to do that. The C of water is 4,180 joules per kilogram degrees Celsius. Ti for the water, what is it this time? 18 degrees. And the final temperature is going to be the same because they're in equilibrium. So that's 22. You can even calculate your delta T now. So in this case, it's going to be 78, and this one is going to be 4. Just give me a moment, sorry. Need to let the dog out. Probably jump off in another couple of minutes and go get the dog back, but that's all right for now. Let's continue. Where were we? We're trying to find the specific heat capacity. So Q is equal to MC delta T. If I'm looking at these, I already know, I don't know what Q is. We aren't able to figure it out because we don't know C, we don't know Q. So we can't do anything fully with just the metal. If we take a look at the water, we have all of our information. Q is equal to MC delta T, and we can figure that out, which is good. I can see that there's an equivalent relationship here. And we already did this before, that Q lost is equal to Q gained. All right, so the energy that the metal has lost has been gained by the water. So we actually don't need to write Q anymore. We can just substitute that Q is equal to MC delta T. MC delta T. But maybe we want to be a little bit more specific, because this side, the left-hand side over here, this is going to be the metal. Metal metal, specific heat capacity in the mass, metal. Oh, no. The right side is the water. And now we should be able to do something. Let's take a look. So the mass of our metal, in this case, we're using kilograms. Oh, actually, let's take a look. It's the specific heat capacity in joules per kilogram. Cool. So our mass is 0.00554. We don't know C. We know delta T is 78. And then I'm going to move this down so I've got a little bit more room. Just like that. I missed the L, classic. Move that down. All right. The mass of my water is equal to, oh, stop scrolling. No, there we go. 0.149. 0.149. My specific heat capacity of water is 4,180. My difference in temperature is 4. Okay, now all we have to do is divide this on both sides. 4, that's a terrible 4, times by 78, and do that on both sides. And you remember, you can simplify stuff. You don't have to put all of this in the calculator. However, it will not matter. As long as you're putting it in right, I suppose. What is going on? Right, that cancels, that cancels. All we're left with is C. So 0.149 times by 4,180 times by 4. Okay, so you could separate that as 2,491.28 divided by our bottom number, which is 0.00554 times by 78. So it's 0.43212. Remember to use as many decimal places while you're working. Only round the last answer. 2,491.28 divided by 0.43212 gives us an answer that C is equal to 5,765.25 joules per kilogram degree Celsius. So that is what our metal's specific heat capacity is. That is the number you would put in and round it to 2 decimal places, which I've already done. Great. We're almost done. Okay, for this one right here, and then I'll come back to this one. We're asked to identify the relationship between the amount of heat and the mass of the substance. Now, we already spoke about this in class, but in case, I think everyone was there yesterday. Yeah, we all were, so hopefully I don't need to go over this too much. Number one, you're asked to identify the relationship or the overall trend. Number one, I want to see 2 things. Type of function, direction. I'm just going to let the dog back here. Sorry about that, he's still a puppy. Okay, the direction is the easiest one to look at. As we increase in our x, is our y increasing as well? So in this case, this is our x, this is our y. Independent, dependent. Now I can see 84 is increasing, 21 is also increasing, so therefore this is a positive relationship, or directly proportional. Now the type of function, that can be a little tricky. There's a couple of ways you can do it, as we discussed in class. You could talk about the factors, because you see here, we need to use evidence from the table. I can see that that's approximately got a factor of 9, the factor being the multiple. It's a little bit more than double, so times by like 2. If I look over here, this is also times by about 2. All right, so that's got a pretty consistent factor. That's one way you could do it. And we could look at if they're consistent. Now, are they consistent? No, this is not times by 2. Well, sometimes that would work as a hack. Maybe not always. There's many different ways we could look at it. And maybe that'll be more helpful if it was maybe quadratic, for example, the factor. Are they continuously doubling all the time? But they're not. So it must be something else. So instead, maybe we could look at the difference. So instead, between here and here, I'm adding about 90. So plus 90. If I go to here, I have also added about 90. It's the difference, okay? If we look over here and here, I've got that's about 20. And if I look between here, that's also about 20. So between two sets, their differences are the same on both sides. We've got a constant difference. And what that means in this case is that our function is going to be linear. And if you're still not convinced, remember that a linear function has got a constant gradient. You could actually calculate the gradient for different points. So between these 2 points, these first two, rise over run, our rise is 20. So over here, m is equal to rise over run. I'm just going to start substituting. And rise is 20. That's our y over here. Our run is 90, so 20 over 90. And if I look at the second point, it's also 20 over 90. 20 over 90. So that gradient is the same, which tells me that this type of function is linear. All right, so I've identified the overall trend. It's a positive linear relationship, and the evidence that I've used, you would incorporate something into your response. So you might look at the factors if it was maybe a quadratic relationship. You could also look at the difference, or you could also look at the gradient as the last option. But of course, there are many, many of the ways we could look at this. It's all about finding the way that is going to be fastest. And our lucky last question. Okay, what are we doing? We are predicting the total amount of energy required to increase its temperature from the initial temperature of 12 degrees, that must be 12, up to 169. So if I look at my graph, it's maxing out at about, 125. So we wanted to get all the way somewhere over here, and that's going to map up at 169. So we want to know what is the total amount of energy. Predict the total amount of energy. All the way across. What is Q? Okay, well, if we're doing total amount of energy, you're probably thinking to yourself, Q is equal to mc delta T. And that's a great thought to have. Love that thought. However, if we try to do this, well, let's take a look. Do we have the mass? We do. It's m equals to 0.25 kg. Do we have C? No, we do not. How unfortunate. Ti, we can see is 12, and we want to get it to a final temperature of 169. But we don't have C. However, we got this giant graph. Surely that can help us figure out C. And it surely can. All right, instead of doing this, we're going to put that on pause, and we're going to instead use this graph to calculate C. Now, you can use any different points along this entire function. And you could use between here and the initial. You could use halfway. And here, like, it doesn't matter. As long as you've got 2 points, you can calculate its gradient because the gradient is proportional to C. Now, I would suggest using the easiest numbers you've got. Because we know that's there, this is 0, 12. That's that coordinate. The other thing I would recommend is looking for any corners. So we can see it cuts through a corner right there. That's probably a pretty good one to choose. You don't have to, but it just makes our life that much easier. So we've got 2 coordinates now. Between here, okay, I can actually calculate now my difference in temperature, and I can also calculate the amount of energy. It's equal to 6,000. So instead, I'm going to calculate C. Calculate C first. My energy between these 2 points, I'll even say a bit of math language. Consider the coordinates 0, 12, and what's our other one? 6,060. Where the x in this case is our energy, and then our y is our temperature. Okay, so our difference in Q, well, that's going to be 6,000 minus 0, which is 6,000. So that's the number of joules that we're going to be using for this example. So Q, I've got Q, I know M, don't know C, and we need a delta T. Delta T, oh, struggling to scroll down, there we go. TF minus TI. So we've got a final temperature of 60 in this new example, these new coordinates I've chosen. Remember, you could choose anything. I've just chosen some easy ones. And that's going to minus and be 48 degrees Celsius. And now I can use this to calculate C. Q is equal to MC delta T. Q is equal to 6,000. M is equal to, I think it was 0.25. Am I right in remembering that? I am. Don't know C yet, but we can calculate it. There we go. Divided by the other numbers that are here on both sides, of course. 2, 5 times 5, 48. Cancels, cancels. And we are left, I'm going to do a little squiggle there, we're left with C. So 6,000 divided by 0.25, and with another 48 there as well. So our C is equal to 500, and our units, let's take a look. We're using kilograms for the mass, so that's going to be joules per kilogram degree Celsius. Remember, we're not done though. We're asked to predict the final or the total amount of energy. So we've found C. Now we can use that in the last little bit. So step 2 over here. Q is equal to mc delta T. We want to know the final energy. We know our mass. We know the specific heat capacity. We calculated it from the table. And the final temperature, that's up to here. Now, there's actually 2 ways you could do this. We could use that our initial temperature is up to here. So then we would go, our final temperature is like 125. And then you could calculate from 125 up to 169. And then you would find the energy for this section, and you would add it together. Up to here, that's 14,000 joules, plus whatever energy you calculate. You could do that. That would work. I'm not going to do that right now, though, because there's definitely an easier approach. Because we start at the number 0, well, why would I bother separating them, right? But let's do this. So our final temperature, our difference in temperature, I'll do it over here, delta T, 169 minus 12, and that is equal to, is my quick math good? No, it's not. It's really, really bad. 157. 157. So this final answer, 0.25 times by 500 times by 157. And remembering, as you're doing these, your numbers could be different. Just be aware of that. Because we're finding energy, the unit is joules. So 19,625 joules. And that is the final answer. I believe I haven't missed any other questions to our revision test. If you have any more questions, guys, feel free to have a chat with me in class. Otherwise, good luck on your revision.